There is a place in our solar system where the sun is no longer a sun, where it shrinks down to something smaller than a coin held at arm's length, where its light, that warm and generous light that fills every afternoon on Earth, fades into something barely stronger than the light of other stars. A place so far from everything familiar that the word distance stops meaning what it normally means. Most people never think about this place. Most people never need to. But it is there, right now, at the edge of everything we have mapped and named and sent spacecraft to explore. And out there, in that cold and ancient darkness, something is moving. Something red. Something that should not be where it is. Something that, when astronomers finally noticed it and traced its path and calculated its orbit, quietly broke several things we thought we understood about how our solar system is shaped. Welcome to Science for Sleep, the place where the universe slows down, and the night gets a little longer, and the questions get a little deeper. Tonight, we are going to travel further than we have ever gone before on this channel. Further than Jupiter, further than Saturn, further than Neptune, the last of the 8 planets, a cold, blue world at the outer edge of the planetary family. Tonight we are going beyond all of that, into the scattered disk, into the deep dark of the outer solar system, to visit a world called Gonggong, a frozen, red, tilted, ancient world orbiting our sun on a path so stretched and so strange that it takes 547 years to complete a single trip around. A world with its own moon. A world whose surface is covered in chemistry so complex and so old that it has been building for 4.5 billion years. A world whose very existence raises questions that astronomers are still trying to answer. If these slow journeys through deep space have become part of your nights, if Science for Sleep has kept you company in the quiet hours, a subscription to this channel costs you nothing and means everything. The button is just below this video. It will take you 2 seconds, and then we can go. Tonight, we explore Gonggong, and we are going to take our time. Let us begin the way all good journeys begin. From the beginning, from here, from Earth. You are here right now, on a planet that orbits the sun at a distance of roughly 150 million kilometers. Astronomers call that distance 1 astronomical unit, your 1 astronomical unit. It is the baseline measurement, the unit against which all other distances in the solar system are measured. The moon is about 0.0026 astronomical units away, close enough that we sent humans there and brought them back safely. Mars, at its closest, is about 0.5 astronomical units away, close enough that we have sent dozens of spacecraft and driven rovers across its surface for years. Jupiter is roughly 5 astronomical units from the Sun, 5 times our distance. The Voyager spacecraft reached it in about 2 years. Saturn is around 10 astronomical units. Uranus, 19 astronomical units. Neptune, the outermost planet, orbits at about 30 astronomical units. These are the planets, the 8 worlds that form the core of our solar system, the ones that appear in every textbook and every classroom poster. And most people assume that beyond Neptune, the solar system essentially ends, that there is a boundary, vague but real, past which there is nothing much. Just open space, eventually giving way to the vast emptiness between star systems. This assumption is understandable. It is also wrong. Beyond Neptune, the solar system does not end. It continues for an enormous distance, filled with objects that most people have never heard of, moving in orbits that follow rules quite different from the neat, flat, nearly circular paths of the 8 planets. The first region beyond Neptune is the Kuiper Belt, a broad zone of icy objects extending from about 30 astronomical units to roughly 50 astronomical units. Pluto lives here. So do Eris, Makemake, Haumea, and thousands of smaller bodies. The Kuiper belt is somewhat like the asteroid belt between Mars and Jupiter, but larger, more distant, and composed primarily of ice rather than rock. Beyond the Kuiper belt, things get stranger. The scattered disk begins. And this is where Gonggong lives. The scattered disk is not a neat ring like the Kuiper belt. It is a population of objects on wild, tilted, stretched orbits that carry them far above and below the flat plane where the planets travel, and out to enormous distances from the Sun. Some scattered disk objects come relatively close to the Sun at their nearest point, then swing out to distances of hundreds of astronomical units at their farthest. These objects are scattered, flung outward, displaced from wherever they originally formed by gravitational interactions, primarily with Neptune, during the early and chaotic history of the solar system. Gonggong is one of these displaced worlds, and its orbit is one of the most extreme among all the named bodies in the solar system. At its closest point to the Sun, its perihelion, Gonggong comes to about 33 astronomical units, slightly farther than Neptune. For a brief window in its 547-year journey, it is in the neighborhood of the outer planets, relatively speaking. But then it swings outward, and it keeps going, past 40 astronomical units, past 50, past 60, past 70, past 80. At its farthest point, its aphelion, Gonggong, reaches approximately 101 astronomical units from the Sun, 101 times the distance between Earth and the Sun, roughly 15 billion kilometers from the center of our solar system. At that distance, the Sun delivers about 10,000 times less energy than it delivers to Earth. The surface temperature falls to somewhere around minus 230 degrees Celsius. The orbital velocity is so slow that Gonggong barely seems to move at all against the background stars, even over years of observation. And most of its 547-year orbit is spent out there in that cold extreme, close to perihelion for a relatively brief window, then slowly arcing outward again into the deep dark. Right now, Gonggong is on its way out. Its last perihelion was in 1857, the year before Darwin published On the Origin of Species, the year that the Indian Rebellion began, the year the Atlantic Telegraph Company was founded. Since then, for nearly 170 years, Gonggong has been moving away from the Sun, getting colder, getting dimmer, getting harder to see even with the best telescopes we have. Its next perihelion will not come until approximately the year 2407, nearly 4 centuries from now. No one alive today will see it return. This is the world we are visiting tonight. And it gets stranger still, because Gonggong does not just travel far. It travels tilted. The 8 planets of the solar system all orbit in roughly the same flat plane. This plane is called the ecliptic. It exists because the solar system formed from a rotating disk of gas and dust, and objects that formed within that disk naturally orbit within it. Deviations from this plane exist, but they are modest. Mercury tilts about 7 degrees. Most planets tilt just a few degrees. Gonggong tilts 30.7 degrees from the ecliptic. 30 degrees. That is not a small deviation. That is not a rounding error in the mathematics of formation. That is a world that has been significantly displaced from wherever it originally formed, pushed onto an orbit that carries it high above and below the plane where everything else travels. And this tilt, combined with its extreme distance and its stretched elliptical path, is what makes Gonggong's orbit one of the most scientifically interesting in the known solar system. Because that orbit is telling us something. Something about the forces that shaped the outer solar system. something about what may still be out there, further than any telescope has clearly seen. We will get to that in time. But first, we need to understand how Gonggong was found, because the story of its discovery is, in its own quiet way, as interesting as everything that came after. In 2007, an astronomer named Megan Schwamb was working through archival telescope data at Palomar Observatory in California. She was part of a team led by Mike Brown, one of the most prolific discoverers of outer solar system objects in the history of astronomy. The same astronomer whose work on Eris led directly to the reclassification of Pluto as a dwarf planet in 2006. The method they used was straightforward in principle, though painstaking in practice. Take an image of a patch of sky. Come back a few days later and take another image of the same patch. Compare the two images carefully, pixel by pixel if necessary, looking for anything that is moved. Stars do not move. Galaxies do not move. Not on the time scale of days. But objects in our solar system do. They travel around the sun. They shift position against the fixed background of distant stars. And if you know what you are looking for, if you have experience reading these images and distinguishing genuine moving objects from artifacts and noise, you can find worlds that no human eye has ever seen before. On July 17, 2007, the data showed a faint point of light that had shifted position between images. It was slow, barely moving. But it was real. The object was catalogued under the designation 2007 OR10, a purely administrative label, the kind assigned to every newly discovered minor planet until something more is known about it and a permanent name can be given. Initial calculations of its brightness suggested it was large, larger than most objects found in that region of the sky, possibly large enough to qualify as a dwarf planet. But at first, nobody was particularly excited. The outer solar system is full of objects. Many are faint, many are poorly understood. Many get catalogued and then sit in databases for years before anyone gets around to studying them in detail. 2007 OR10 joined that quiet queue. It waited, the way distant worlds do, patiently, in the dark. Over the following years, better observations accumulated. The object's orbit was refined, its size was estimated more carefully. By around 2016, estimates placed its diameter at roughly 1,230 kilometers, making it one of the largest known objects in the solar system beyond Neptune, large enough that it almost certainly had enough gravity to pull itself into a roughly spherical shape, large enough to qualify under the definition of a dwarf planet, though it has not been formally classified as one by the International Astronomical Union. And there was something else. Something that nobody had expected when the object was first discovered. 2007 OR10 was red, not slightly red, not reddish in the way that many outer solar system objects are slightly reddish. Deeply, strikingly, unusually red. Once red in a way that immediately told astronomers something important about what was on its surface and how it had been spending the last 4.5 billion years. The team had initially nicknamed it Snow White, an ironic choice given that they expected it to be bright and icy like some other large Kuiper Belt objects. When the true color emerged from the data, the nickname was quietly dropped. Snow White was not white. It was one of the reddest large objects ever found in the outer solar system. And that redness is a story in itself. The object was large. It was red. It was on an extraordinary orbit. And it had been sitting in telescope data, unrecognized and unnamed, for years before anyone fully appreciated what it was. That changed in 2019. because by then, the team had another piece of information. 2007 OR-10 had a moon. Though discovered in archival images from the Hubble Space Telescope, the moon was small, roughly 150 to 250 kilometers in diameter. It orbited 2007 OR-10 at a distance of about 24,000 kilometers, taking approximately 25 days to complete one orbit. The existence of a moon changed everything about what could be calculated. When you watch a moon orbit a body, you can use the laws of gravity to calculate the mass of the body it orbits. Mass, combined with size, gives you density. And density tells you what a world is made of, roughly what mix of rock and ice makes up its interior. With the moon's orbit now measured, the team finally had the numbers they needed. And with numbers came a name. In 2019, the team decided that 2007 OR-10 was significant enough, large enough, and interesting enough to deserve a proper name rather than an administrative catalog number. They put it to a public vote. 3 candidate names were offered. The vote ran online. Anyone could participate. 280,000 people voted. 46% of them chose the same name. Gonggong, the water god, the god of chaos, the deity from ancient Chinese mythology who, according to legend, lost a great battle, struck a mountain in rage, tilted the earth on its axis, and flooded the world. The International Astronomical Union officially confirmed the name on February 5, 2020. And with that confirmation, 2007 OR-10 became Gonggong, the first major solar system body to carry a Chinese mythological name. Its moon was named Xiangliu, after the 9-headed poisonous serpent that served as Gonggong's minister in the same mythology. 2 names from an ancient story, given to 2 worlds at the edge of our solar system. Worlds that had been orbiting in silence for 4.5 billion years, long before any human civilization existed to tell any story about anything. Long before the mythology that now carries their names was ever spoken aloud. And yet the names fit. They fit in a way that goes beyond coincidence. Because Gonggong, the dwarf planet, is tilted, displaced, chaotic in its orbit, flung far from where it formed onto a path that breaks the rules of the flat, ordered solar system. Just like the god it was named for. A world that struck something and was thrown sideways. A world that tilts. A world that does not follow the pattern. That is where we begin. That is Gonggong. And we have barely started. There's a story that has been told in China for thousands of years. It begins, as many ancient stories do, with a conflict. 2 powerful beings, each claiming dominion over something vast, each unwilling to yield, each certain that the other was wrong. The details vary depending on which version you read, which dynasty recorded it, which storyteller shaped the telling. Ancient mythology is not a fixed text. It is a living tradition, passing through centuries, accumulating variations, shaped by the concerns and the imagination of every generation that carries it forward. But the core of the Gonggong myth remains consistent across its many versions. Gonggong was a water god, a deity associated with floods, with the sea, with the destructive and uncontrollable power of water in its most dangerous forms. Not the gentle rain that feeds crops, not the river that sustains a city, but the flood, the inundation, the water that rises and does not stop rising until everything familiar is submerged. In some versions of the myth, Gonggong challenged Zhurong, the god of fire, for supremacy. In others, the challenger was different. The cause of the conflict shifted slightly. But in nearly every telling, the outcome was the same. Gonggong lost, and in his rage at losing, in the fury of a being who had fought for dominance and been denied it. He did not accept defeat quietly. He turned. He struck. He threw himself against Buzhou Mountain, one of the pillars that in ancient Chinese cosmology held up the sky. And the impact was so violent, so absolute, that the pillar broke. The sky tilted. The earth tilted with it. The waters of the world flooded southward. Whilst the stars shifted in their positions. The sun and moon changed their courses. Everything that had been ordered and balanced was thrown into chaos by a single act of furious, unstoppable force. This is the God that 280,000 people voted to give their name to a world at the edge of the solar system. And when you understand what Gonggong the dwarf planet actually does, when you understand its orbit and its tilt and its displacement from the ordered flat plane where everything else travels, the choice feels less like mythology and more like recognition. Because Gonggong the world is also tilted, also displaced, also a thing that does not follow the pattern. A world that was thrown, not by rage, but by gravity, not by myth, but by the real and ancient violence of planetary formation, out onto an orbit that breaks the rules of the solar system, the same way the god broke the pillars of the sky. The name is not a coincidence. It is an insight. To understand why the name fits so perfectly, we need to spend a little more time with the orbit itself. Gonggong's eccentricity is 0.50. That is not a small number. That is not a slight deviation from circular. An eccentricity of 0.50 means Gonggong's orbit is significantly stretched, significantly elliptical, pulled into a shape where the difference between its nearest and farthest points from the Sun is enormous. At perihelion, 33 astronomical units. At aphelion, 101 astronomical units. The ratio between those two distances is about 3:1. When Gonggong is at its closest to the Sun, it is 3 times closer than when it is at its farthest. Now tilt that ellipse. You tip it 30 degrees away from the flat plane where the planets travel. Now imagine a world traveling along the edge of the tilted, stretched ellipse, spending most of its time in the cold outer regions, arcing slowly through darkness, then swinging back inward toward the Sun for a relatively brief, close approach before heading outward again. That is Gonggong's path through space. And there is one more detail about this orbit that matters, one that connects Gonggong directly to the planet that shaped it. Gonggong is in orbital resonance with Neptune. Resonance is one of the most important and most elegant concepts in planetary science. It describes a situation where 2 orbiting bodies complete their orbits in a ratio of whole numbers, so that their gravitational interactions repeat in a regular, predictable pattern. Gonggong is in a 3:10 resonance with Neptune. For every 10 orbits Neptune completes, Gonggong completes exactly 3. This resonance is not a coincidence. It is a fingerprint. It tells us that Gonggong did not always have the orbit it has now. At some point in the distant past, Neptune's gravity interacted with Gonggong repeatedly, at regular intervals, in a way that gradually shifted its orbit, stretching it, tilting it, pushing it into the configuration we observe today. Gonggong's wild orbit is Neptune's work. Neptune threw it, just as Gonggong the god threw himself against the mountain. The mythology and the physics rhyme in a way that feels almost deliberate, though of course it is not. It is simply that the humans who chose the name were paying attention. They saw the parallel. They saw a world displaced by a great force and thrown onto a tilted, chaotic path, and they reached for the story that matched. There is a boundary in our solar system that most people treat as an ending. Neptune, the 8th planet, the last one on the list. the deep blue world that sits at the outer edge of what most people consider the solar system proper. Orbiting the Sun at a distance of roughly 30 astronomical units, taking 165 years to complete a single trip around. Most people, when they picture the solar system, picture the 8 planets arranged in their orbits around the Sun. Maybe they add the asteroid belt between Mars and Jupiter. Maybe they include Pluto. And then the image ends. This picture is wrong. Not wrong in its details, but wrong in what it leaves out. Because beyond Neptune, the solar system does not end. It does not even begin to thin out into nothing for an enormous distance. What lies beyond Neptune is a complex, layered, populated region of space containing hundreds of thousands of objects, possibly millions, ranging in size from dust to worlds nearly as large as Pluto, all orbiting the Sun in a variety of paths, from the relatively ordered to the spectacularly chaotic. The scattered disk is not a neat ring like the Kuiper belt. It is a population of objects on wild, tilted, stretched orbits that carry them far above and below the flat plane where the planets travel. Gonggong is one of these displaced worlds. The solar system we see today is not the solar system that formed 4.5 billion years ago. The planets were not always where they are now. This is one of the most important and most counterintuitive findings of modern planetary science. In the beginning, one after the Sun formed from a collapsing cloud of gas and dust. The remaining material around it formed a rotating disk. Within that disk, solid particles clumped together, grew into pebbles, pebbles grew into boulders, boulders grew into planetesimals, and planetesimals grew through collision and gravitational attraction into the planets. But the positions of those planets, as they formed, were not quite the same as their positions today. Neptune's outward migration was particularly consequential for everything in the outer solar system. As Neptune moved outward, it swept through the population of objects that had formed in the region between roughly 20 and 30 astronomical units. Some of those objects were captured into resonances with Neptune and carried outward with it. Some were pushed outward, and their orbits were stretched into the eccentric, Yuan high-inclination paths we see in the scattered disk. Gonggong is one of these, a refugee of Neptune's migration, a world that formed somewhere in the region of 20 to 30 astronomical units, in a zone that was warmer than its current location, and was then thrown outward onto the orbit it travels today. Let us follow Gonggong through one complete orbit. We will begin at perihelion. The year is 1857. On Earth, this is a year of considerable human activity. The Indian Rebellion is underway. The financial panic of 1857 is rippling through markets. Flaubert published Madame Bovary that year. Baudelaire published Les Fleurs du Mal. All of this human noise and complexity and consequence is happening on Earth. And on Gonggong, there is silence. There has always been silence. At perihelion, Gonggong is approximately 33 astronomical units from the Sun. At 33 astronomical units, the sunlight reaching Gonggong is about 1,100 times weaker than the sunlight reaching Earth. The surface temperature, even at this closest point, is somewhere around minus 220 degrees Celsius. This is Gonggong's warmest moment, and it is extraordinarily cold. Then Gonggong begins to move away. Right now, as you listen to these words, Gonggong is approximately 89 astronomical units from the Sun. It has been moving away from its 1857 perihelion for nearly 170 years. And it still has not reached its aphelion. Its aphelion is at 101 astronomical units. It will reach that point sometime around the year 2134, 108 years from now. after which it will finally begin its long, slow return toward the Sun. Its next perihelion will be approximately in the year 2407, 450 years from now. Every human civilization that currently exists will have transformed beyond recognition, or ended, or been replaced by something new before Gonggong makes its next close approach to the Sun. Gonggong's orbit is not just extreme in its distances and its timescale. It is also extreme in what it means for the world itself. Consider the experience of a year on Gonggong. On Earth, a year is the time it takes to complete one orbit around the Sun. 365 days. A cycle that shapes our calendars, our seasons, our biology. On Gonggong, a year is 547 Earth years. This means that if Gonggong had seasons at all, those seasons would each last for over a century. Summer on Gonggong lasts longer than any human civilization has ever existed in a continuous, recognizable form. Winter on Gonggong is a state that begins before recorded human history and ends after it. And then there is the question that the orbit raises. The question that connects Gonggong not just to Neptune, but to something further. Something we have not yet confirmed. Something that remains one of the most significant open questions in planetary science. Gonggong's orbit is extreme, but Gonggong is not alone in having an extreme orbit. When astronomers looked carefully at the orbital parameters of these extreme distant objects, at the direction their orbits were tilted, at the orientation of their closest approaches to the Sun, they noticed something. A pattern. Not a perfect pattern, not an exact alignment, but a clustering, a tendency for these extreme orbits to point in similar directions. Randomness does not cluster, and if these orbits were the product of random scattering, they would be distributed evenly across all orientations. But they are not spread uniformly. They cluster, and clustering implies a cause. In 2016, astronomers Konstantin Batygin and Mike Brown published a paper proposing an explanation for this clustering. They called it Planet 9, a massive, distant, unseen planet, possibly 5 to 10 times the mass of Earth, orbiting the Sun at a distance of perhaps 400 to 800 astronomical units, on a highly eccentric and inclined orbit, invisible to current telescopes because at that distance, it would be extraordinarily faint and slow-moving. A planet whose gravitational influence, acting over hundreds of millions of years, had slowly herded the orbits of scattered disk objects into the aligned configuration we observe today. A planet we have never seen, but a planet whose existence, if real, would be written into the paths of every distant object that orbits in its gravitational shadow, including Gonggong. Whether Planet 9 exists remains unknown. The evidence is suggestive but not conclusive. Searches are ongoing. But the possibility is real, and it is worth sitting with. The idea that the solar system may have a ninth planet, undiscovered, hiding in the darkness at distances we have never properly surveyed, shaping the orbits of the worlds we can see from the darkness of its own vast, slow orbit. If Planet 9 exists, then Gonggong is one of the clues, one of the breadcrumbs it has left in the paths of distant worlds. A red world at the edge of everything, following an orbit that points, very quietly, towards something we have not yet found. Or if you could stand at a telescope powerful enough to resolve Gonggong as something more than a point of light and look at it carefully, the first thing you would notice is the color. Red. Not the red of a sunset, which is warm and orange-tinged and carries associations of warmth and endings and beauty. Not the red of Mars, which is the dusty iron oxide red of a rocky desert world. Something deeper, something darker, a red that sits closer to brown in some regions, more vibrant in others. The kind of red that suggests age. The kind of red that has been building for a very long time. Gonggong is one of the reddest large objects in the solar system. And when the Discovery team first confirmed this color, it surprised them. They had not expected red. They had expected something closer to white. To understand why Gonggong is red, you need to understand a class of chemical compounds called tholins. Tholins are not a single compound. They are a family of complex organic molecules, loosely defined, that form when simple carbon-containing molecules like methane and nitrogen are exposed to energy in the form of ultraviolet radiation or charged particle bombardment over long periods of time. The name was coined by the astronomer Carl Sagan and his colleague Bishan Kare in 1979. Sagan derived it from the Greek word tholos, meaning muddy or murky, a fitting description for the dark, reddish-brown, sticky substances that form in laboratory experiments when you bombard simple organic gases with radiation. In the outer solar system, the conditions for tholin formation are ideal. There is no shortage of radiation. The sun, even at the enormous distances of the scattered disk, produces a constant stream of ultraviolet photons. And the solar wind, a flow of charged particles streaming outward from the sun, as well as cosmic rays from outside the solar system entirely, provide a continuous bombardment of energetic particles that can break molecular bonds and drive chemical reactions. There is no shortage of time. The outer solar system has existed for 4.5 billion years, and the objects within it have been exposed to this radiation for essentially that entire period. The red color of Gonggong is the color of 4.5 billion years of radiation chemistry. It is the color of time. Tholins are organic compounds, and organic compounds are the category of chemistry that, on Earth, forms the basis of all known life. Carbon-based, hydrogen-rich, nitrogen-containing molecules are the foundation of amino acids, of proteins, of nucleic acids, of the entire biochemical machinery that makes living things work. Tholins are not life. They are not even the direct precursors to life in any simple sense. But they are evidence that the raw material for complex organic chemistry exists throughout the outer solar system. That the building blocks are not rare. That the universe, given time and radiation and simple starting materials, spontaneously produces complex organic molecules in enormous quantities. In December 2021, the James Webb Space Telescope launched and began its journey to the second Lagrange point, a gravitationally stable location about 1.5 million kilometers from Earth on the night side. Among the solar system targets that Webb turned its instruments toward in its early science program were several distant trans-Neptunian objects, including Gonggong. Webb found several things: water ice, confirmed, carbon dioxide ice, present on the surface, and ethane ice. This was the finding that drew the most scientific attention. Ethane is a simple hydrocarbon. Its chemical formula is C2H6, 2 carbon atoms, 6 hydrogen atoms. On Earth, it is a component of natural gas. At Gonggong's surface temperatures, it would exist as a solid. The interesting thing about ethane on Gonggong is not that it is there, but what it implies about what was there before. Ethane in the outer solar system is, in most models, a product of the radiation processing of methane. Methane, CH4, is one of the simplest organic molecules. When methane is exposed to ultraviolet radiation and energetic particle bombardment over long periods of time, the radiation breaks molecular bonds. Some of those recombinations produce ethane. So ethane ice on Gonggong's surface is evidence of a long history of methane irradiation. It is a decay product, in a chemical sense. evidence that methane was once present and has been slowly converted by billions of years of radiation into more complex compounds. But here's the puzzle. If Gonggong originally had methane ice on its surface, where is the methane now? Webb found no clear evidence of fresh methane ice on Gonggong's surface. This absence is informative. It tells us something about Gonggong's size, its gravity, and its ability to retain volatile compounds over geological time. Pluto is large enough to retain methane. Its surface is covered in methane frost, and it has a thin but detectable methane atmosphere. Gonggong is smaller. Its estimated diameter of around 1,230 kilometers is substantially less than Pluto's 2,377 kilometers. Its surface gravity is lower. Its escape velocity is lower. Gonggong sits right at the edge of the size range where methane retention becomes possible. It is a world living at a threshold, just barely too small to hold on to the most volatile of its original surface ices over the full age of the solar system. Every world spins. It is one of the most universal behaviors in the solar system, the consequence of how things form. But rotation rates vary enormously. Jupiter completes one rotation every 9.9 hours. Many smaller solar system objects spin every 4 to 10 hours. So when astronomers measured Gonggong's rotation period and found that it spins once every approximately 22 hours, they noticed something immediately. 22 hours is slow, not dramatically slow by planetary standards. But for a trans-Neptunian object of Gonggong's size, 22 hours is unusually slow. Something slowed it down. And when you ask what could have slowed Gonggong's rotation, the most compelling answer involves Xiangliu. When a moon forms or is captured by a parent body, the two objects immediately begin gravitationally influencing each other in ways that go beyond simple orbital motion. The gravity of the moon raises a tidal bulge on the parent body. If the parent body rotates faster than the moon orbits, the tidal bulge does not point exactly at the moon. The rotation of the parent body carries the bulge slightly ahead of the moon's position. The moon is gravitationally attracted to the bulge, which is slightly ahead of it. This forward pull transfers angular momentum from the parent body's rotation to the moon's orbit. The parent body spins down. The moon's orbit expands. This process is tidal dissipation. On Earth, this process has been slowing our planet's rotation for billions of years. 4.5 billion years ago, Earth's day was only about 6 hours long. It has been lengthening ever since. Tidal dissipation on the Gonggong-Xiangliu system has been operating for billions of years, and the result we observe, a 22-hour rotation period, suggests that the process has been running long enough to significantly slow Gonggong's spin, but has not yet completed the full synchronization. The discovery of Xiangliu itself is a story worth telling. When Gonggong was first identified in 2007, it was just a moving point of light in telescope images. No one knew it had a moon. The discovery was not made during a dedicated observation of Gonggong for the purpose of finding moons. It was made in archival data. Images of Gonggong that had already been taken by Hubble for other purposes. Images that were sitting in the data archive waiting to be analyzed in detail. When astronomers went back and looked at those archival Hubble images carefully in 2016, they saw it. A faint companion point of light, close to Gonggong, moving with it against the background stars, clearly gravitationally bound. Xiangliu. It had been there in the data for years, unnoticed, waiting in the way that discoveries often wait, for someone to look carefully enough. The Pluto-Charon system is one of the most unusual in the solar system. Charon is enormous relative to Pluto. The ratio is roughly 1 to 2. No other planet-moon pair in the solar system comes close to this ratio. Pluto and Charon have reached the end state of tidal evolution. They are mutually tidally locked. Pluto always shows the same face to Charon. Charon always shows the same face to Pluto. They orbit each other every 6.39 days, and both rotate once every 6.39 days. From Pluto's surface, Charon hangs in the sky, enormous, and it does not move. It neither rises nor sets. It simply sits there, always in the same position relative to the horizon. This is the end state of tidal evolution for a binary system. This is what Gonggong and Xianglu are slowly moving toward. Not quickly. Not on timescales that would be perceptible to any civilization monitoring from Earth. But the direction of travel is clear. The physics is operating. And eventually, across timescales measured in billions of years, Gonggong and Xianglu will reach the same configuration that Pluto and Charon already inhabit. A permanent mutual embrace. Two faces always turned toward each other. Two worlds that have, in a gravitational sense, become one system. There is something worth pausing on here. The two bodies are exchanging information about each other through gravity. Every moment, Xiangliu's gravity tells Gonggong how it is spinning relative to Xiangliu's orbital motion. Every moment, Gonggong's gravity tells Xiangliu whether it is circular or elliptical in its orbit. The two bodies are in a conversation that started billions of years ago and has not ended. The conversation is very simple. It has only one message, repeated endlessly. Slow down. Come closer. Turn toward me. And Gonggong is listening. Slowly. At a rate completely imperceptible on any human timescale. But listening. Everything we have discussed so far has been visible, in one sense or another. The orbit, the surface color, the rotation, the moon. But now we go somewhere that no instrument has yet directly measured. Inside. Into the interior of Gonggong, a place we can only know through inference, through the indirect signatures of gravity and density and surface chemistry. Through models built on physics and constrained by what limited observations we have. The first question to ask about any planetary interior is whether it has differentiated. Differentiation is the process by which a forming body separates into distinct layers. Heavy materials, primarily iron and other metals, sink toward the center under gravity. Lighter silicate rocks form a mantle above that. The lightest materials, water ice and organic compounds, rise to form the outer layers and surface. Whether Gonggong differentiated depends on whether it ever got hot enough, for long enough, for its interior to melt and allow dense materials to sink and lighter ones to rise. The heat sources available to early Gonggong were two. The first was accretional heat, when objects collide and merge during the formation of a planetary body. The kinetic energy of the collision is converted to heat. The second was radioactive decay. The early solar system contained significant quantities of short-lived radioactive isotopes, particularly aluminum-26 and iron-60. These isotopes decay rapidly on geological timescales, releasing heat as they do. Gonggong's size places it in an interesting region. At roughly 1,230 kilometers diameter, it is large enough that accretional heat and early radiogenic heating could have been significant. Models suggest that objects in this size range may have experienced partial melting of their interiors during the first few 100 million years of the solar system's history. The water ice on Gonggong's surface is one of the most important clues about its interior history. Fresh, bright water ice on the surface of an ancient world means the ice was put there recently, relatively speaking, in planetary terms. The most plausible mechanism for putting fresh water ice on the surface of a world in the cold outer solar system is cryovolcanism. Cryovolcanism is volcanism, But instead of molten rock erupting from the interior, it is liquid water or water-ammonia mixtures that erupt. In the outer solar system, where temperatures are so low that water is normally solid, liquid water can only exist if the interior is warm enough to melt it. If Gonggong's interior melted enough to produce liquid water at depth, that water could have found pathways to the surface, erupting and freezing immediately on contact with a cold vacuum, depositing a layer of fresh ice. Whether Gonggong retains any liquid water in its interior today is a question with an almost certainly disappointing answer. Probably not. The short-lived radioactive isotopes that drove the early heating have long since decayed. The longer-lived isotopes produce heat, but at much lower rates. For a body of Gonggong's size, the current heat production from long-lived radioactive decay is likely insufficient to maintain liquid water at any depth. The interior has almost certainly frozen. What was once, perhaps, a subsurface liquid water layer in Gonggong's early history has long since solidified into ice. The cryovolcanism has ceased. The interior is cold and rigid and geologically inert. Gonggong's interior is not a place of ongoing activity. It is a record of past activity, a frozen snapshot of a world that was once, briefly, warm enough to be interesting in the geological sense, and has been cooling ever since. On Earth, a season lasts 3 months. Winter arrives. The days shorten, the temperatures drop, the natural world adjusts, and then, with the reliability that comes from the tilt of a planet and its annual journey around the sun, the season ends. On Gonggong, if seasons exist at all, a single season lasts longer than any human civilization has continuously existed in recognizable form. This is not a metaphor. This is orbital mechanics. Gonggong's 547-year orbit creates a cycle of warmth and cold so slow that the words warmth and cold are almost misleading. Near perihelion, at 33 astronomical units, the surface temperature of Gonggong rises to approximately -220 degrees Celsius. This is the warmest Gonggong gets. Near aphelion, at 101 astronomical units, the surface temperature falls further to somewhere around -230 to -240 degrees Celsius. The difference between perihelion and aphelion temperatures is perhaps 10 to 20 degrees. On Earth, a 10-degree difference in temperature separates a mild autumn afternoon from a cold winter morning. On Gonggong, that same 10-degree difference is the entire range of climatic variation across 5 centuries. The question of whether Gonggong has an atmosphere is connected directly to this temperature variation. An atmosphere requires volatile compounds that can exist as gas rather than solid at the relevant temperatures and pressures. The result, as best we can model it, is that Gonggong's atmosphere, if it can be called that, is extraordinarily thin. Perhaps a millionth of Earth's atmospheric pressure at sea level, or less. Gonggong's last perihelion was in 1857. For 170 years, it has been moving away from the sun, and if any trace atmosphere existed at perihelion, it has been slowly freezing out onto the surface since 1857. Every year, molecules that briefly existed as gas near perihelion have been settling back onto the frozen terrain. The atmosphere, such as it was, has been collapsing for longer than most modern nations have existed in their current form. And it will not return. Not until 2407. Not until 4.5 centuries from now. The concept of a season that outlasts civilizations is one of the stranger gifts that planetary science offers to the imagination. We measure time in human units because that is natural. That is what we evolved to do. Our sense of time is calibrated to heartbeats and sunrises and generations and centuries. But the universe has no such calibration. It operates on whatever timescale the physics demands. Gonggong's 547-year season is not trying to be strange. It is simply what happens when you orbit the Sun at 33 to 101 astronomical units. The strangeness is entirely in the perspective of a creature, us, whose entire experience of time is compressed into a century or less. From Gonggong's perspective, if Gonggong had a perspective, the Sun is simply a light in the sky that slowly brightens over centuries and then slowly dims again. A cycle of imperceptible warmth and slightly less imperceptible warmth, repeating forever. Nothing that happens on the time scale of a human lifetime is meaningful at Gonggong's orbital scale. And perhaps that is, in the end, a restful thought. That somewhere out there, a small red world is completing a journey that began before any currently living person was born and will end after every currently living person is gone. They're indifferent and ancient and perfectly content to continue orbiting for billions of years more. The universe does not rush, and neither does Gonggong. Gonggong is not alone. In the darkness beyond Neptune, there are others. Worlds that share Gonggong's general character, displaced and tilted and eccentric. Worlds that were formed in the inner solar system and thrown outward by Neptune's gravity during the violent early period when the giant planets were still migrating to their current positions. They are scattered disk objects, Neptune's scattered children. Worlds that carry in their orbits the fingerprints of the forces that shaped them. Fossils of the solar system's most chaotic era. Eris is the largest of the known scattered disk objects. Its diameter is approximately 2,326 kilometers, slightly smaller than Pluto, but more massive. Its surface is covered in methane frost so fresh and reflective that it is one of the brightest objects in the solar system. When it was discovered in 2005 by Mike Brown, it was initially thought to be larger than Pluto, which directly triggered the debate that led to Pluto's reclassification as a dwarf planet in 2006. Sedna is the most extreme of the known distant objects. Its perihelion is at 76 astronomical units. Its aphelion is estimated at approximately 937 astronomical units. Its orbital period is roughly 11,400 years. These numbers place Sedna in a different category from Gonggong and Eris. Sedna does not come close to Neptune. Its perihelion at 76 astronomical units is well beyond Neptune's orbital neighborhood. Neptune cannot explain Sedna's orbit. Something else pushed Sedna to where it is. The leading candidates are the Sun's birth cluster, a dense cluster of stars in which the Sun formed during its first few 100 million years, and the possibility of a distant planet, the same hypothetical Planet 9 that Gonggong's orbit also hints at. Quaoar is closer and better known than Sedna. Its surface is remarkably similar to Gonggong's. Red, rich in tholins, evidence of water ice. Similar spectral characteristics. This similarity is informative precisely because Quaoar and Gonggong have different orbital histories. Quaoar has not been scattered onto an extreme orbit. It has remained in the relatively ordered Kuiper belt. Yet its surface chemistry looks similar to Gonggong's. This tells us that the red tholin chemistry is not a consequence of having a scattered disk orbit. It is a consequence of size, composition, and time. Any object of similar size, made of similar material, exposed to similar radiation levels for similar durations, will develop a similar red surface regardless of whether it is in the scattered disk or the classical Kuiper belt. The universe is consistent that way. Same ingredients, same processes, same result. The population of distant outer solar system objects taken together tells a story about the early solar system that we could not read from any single object alone. The early solar system was violent in ways that left permanent marks. When the giant planets migrated to their current positions, they scattered enormous amounts of material outward. Some of this material was thrown out of the solar system entirely. Some was pushed into the Oort cloud. Some was displaced into the scattered disk, onto the eccentric, inclined orbits we see today. Gonggong is one of these survivors. Its orbit, untilted and stretched and resonant with Neptune, is a direct record of what the early solar system did to it. And it has been there ever since. 4.5 billion years of orbiting, of surface chemistry building slowly, of cooling and freezing, and carrying its ancient red terrain through the scattered disk. One 547-year loop after another. Science is often described as impersonal. A process, a method, a system for extracting reliable knowledge from observation and experiment and careful reasoning. And it is those things. But it is also done by people. People who stay late at their computers reviewing archival images. People who notice things that other people missed. People who ask questions and refuse to stop asking them until the answers emerge. The discovery of Gonggong is a human story as much as a scientific one. Ours, and the naming of Gonggong is, in some ways, the most human part of all. In 2019, the team decided that 2007 OR10 was significant enough, large enough, interesting enough to deserve a proper name rather than an administrative catalog number. They put it to a public vote. 3 candidate names were offered. Gonggong, the Chinese water deity associated with floods, chaos, and the tilting of the earth. Hola, a German winter goddess associated with snow and the underworld. Vili, a Norse deity, one of the 3 gods who, in Norse mythology, created the first humans from 2 trees found on a beach. The vote opened. It ran for several weeks. It spread across social media and astronomy communities and general interest science audiences around the world. 280,000 people voted. When the results were tallied, Gonggong had received 46% of the votes. Holly received 34%. Vili received 20%. Gonggong won. The choice feels, in retrospect, almost inevitable. Not because of the vote numbers, though those are decisive, but because of how perfectly the name fits. Gonggong the god tilted the world in a moment of chaotic rage. He struck the pillar of the sky and threw the cosmos into disorder. Gonggong, the dwarf planet, is tilted. Its orbit is disordered. It was thrown outward by Neptune's gravity into a chaotic, eccentric path that breaks the flat symmetry of the planetary disk. When the International Astronomical Union officially confirmed the name on February 5, 2020, Gonggong became the first major solar system body to carry a name drawn from Chinese mythology. And Xiang Liu, the 9-headed serpent minister, followed. On only 2 names from thousands of years of Chinese storytelling, now attached to 2 real worlds at the edge of the solar system, carrying those stories out into a darkness that no human has ever crossed. There is something worth pausing on in the act of naming. A world that has been orbiting the sun for 4.5 billion years does not need a name. It was there before language. It will be there long after language. The orbit does not change when we call it Gonggong, and yet naming matters to us. Names are how we locate things in our understanding. Names are the handles we grip when we try to grasp something vast and remote, and otherwise impossible to hold in the mind. Gonggong, the world, is a force, in the sense that its existence demands understanding. Its orbit is telling us something. Its surface chemistry is a record of ancient processes. Its moon is evidence of a collision and billions of years of gravitational evolution. These things demand to be read. The name invites us to read them. And that is why naming, which might seem like a bureaucratic formality, is actually one of the most human things we do with the discoveries that science gives us. We reach for the story. We always reach for the story. No spacecraft has ever visited Gonggong. As of today, no spacecraft is on its way there. The closest analogy to what a Gonggong mission might look like is New Horizons, the spacecraft that flew past Pluto in July 2015 and then continued outward to visit the Kuiper Belt object Arrokoth in January 2019. New Horizons was launched in January 2006. It reached Pluto after 9.5 years of travel. Gonggong is much further than Pluto. A mission designed like New Horizons, launched today with similar propulsion, would take somewhere between 20 and 30 years to reach Gonggong. A spacecraft launched today would arrive at Gonggong somewhere between 2045 and 2055. The scientists who designed such a mission and fight for its approval and funding today would be in their 70s or 80s, if still alive, when the first images come back. If humans were ever to travel to Gonggong, rather than just send robots, the challenges would be in a different category entirely. The current distance of 89 astronomical units translates to approximately 13.4 billion kilometers. A signal traveling at the speed of light takes approximately 12.4 hours to cross that distance. A round-trip communication with Earth would take nearly 25 hours. No real-time conversation would be possible. Every decision would be local. Every emergency would be handled by the crew with no possibility of guidance from Earth until half a day after they sent the question. The surface, if you landed, would be extraordinary in its desolation. Temperature, approximately minus 230 degrees Celsius. Gravity, approximately 0.07 g, 1/14 of Earth's gravity. Each step would be a slow, deliberate commitment to a surface that could send you floating if you pushed too hard. The horizon would be close. Standing on a flat plain, you would see the world end about 20 to 30 kilometers away. The sky would be absolutely black. The sun would be a brilliant white point of light, far brighter than any star, but not filling the sky the way it fills an Earth afternoon. The shadows it cast would be sharp and deep. Everything not directly lit would be in complete darkness. The stars would be extraordinary. Without atmosphere, without scattered light, without anything between you and the universe. The sky would be a structure, not a scatter of points, but a complex, layered, three-dimensional architecture of hundreds of billions of suns. And somewhere in that sky, Shangliu would drift slowly, a small gray irregular shape against the stars, completing its 25-day orbit, as it has been doing for billions of years. No human being has ever been this far from Earth. Gonggong at 89 astronomical units is 22,000 times further from Earth than the Moon. To stand on Gonggong's surface would be to stand at a distance from home that is currently beyond any human transportation system we have built or are close to building, but not beyond imagination. And then perhaps that is where it starts. With imagination. With the willingness to look at a red point of light in a telescope image and ask what it is, where it came from, what it is made of, and what it would be like to stand on its surface and look back at the faint white star that is our sun. We have traveled a long way tonight, from the familiar warmth of Earth's orbit, outward past the planets, through the asteroid belt, past the gas giants, through the Kuiper Belt, into the scattered disk, to a small red world at 89 astronomical units that most people have never heard of and no spacecraft has ever visited. We have looked at its orbit, its surface, its interior, its moon, its atmosphere, or the near total absence of one, its family of scattered disk companions, the humans who found it and named it. the imagined experience of standing on it. Now we come to the final question. Not what Gonggong is or where it came from, but what it will become, and what it means that it was here at all. Gonggong's future, over the next few billion years, is relatively uneventful by cosmic standards. It will continue orbiting the Sun on its 547-year ellipse. It will reach its aphelion at 101 astronomical units around the year 2134, and then slowly begin its return toward the inner solar system. Its next perihelion will come around 2407, and then it will arc outward again, and return again, and outward again. This cycle will repeat approximately 8.2 million times over the next 4.5 billion years. 8.2 million complete orbits of the Sun, each one 547 years long. During this time, the surface will continue its slow chemical evolution. The tholins will continue to build. The interior will continue to cool, becoming more rigid, more inert, more settled into the deep geological quiet it has already largely achieved. Nothing dramatic, nothing sudden, just time. Vast, unhurried, indifferent time. The one event that will genuinely change Gonggong's situation is not something Gonggong will do. It is something the Sun will do. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to expand into a red giant. Its luminosity will increase enormously. The sunlight reaching Gonggong will increase dramatically. Surface temperatures that currently hover around -230 degrees Celsius may rise by tens or hundreds of degrees. The water ice that has been frozen solid for billions of years may begin to sublimate. For a brief period in geological terms, Gonggong may have a genuine atmosphere, a brief spring on Gonggong after 9 billion years of winter. And then the Sun will complete its red giant phase, shed its outer layers in a planetary nebula, and contract into a white dwarf. The energy reaching the outer solar system will plummet. Gonggong's brief spring will end. The surface will return to its deep cold. And Gonggong will continue orbiting the white dwarf remnant of the Sun, as it has always orbited, patient and indifferent and unchanged in any fundamental way, for billions of years more. Let us step back from the timeline and sit with what Gonggong represents. It formed from the same cloud of gas and dust that formed Earth. Roughly the same time, roughly the same raw materials, the same atoms in different proportions, assembled by the same processes of gravity and collision and chemical accretion. The Earth and Gonggong are siblings, in a sense, born from the same parent. But they went very different ways. Earth stayed warm. It retained water as liquid. It developed an atmosphere. It developed geology. It developed, in a process that remains incompletely understood, life. And life, over billions of years, produced eyes to see with and minds to wonder with and telescopes to point at the darkness. Gonggong went cold. It was thrown outward into the dark. It froze. Its water became ice, and its ice became covered in radiation chemistry, and its interior cooled, and its geology ceased, and it simply continued, loop after loop around the Sun, carrying its ancient red surface through the cold and the silence of the scattered disk. Two worlds, one origin, vastly different fates, and yet here we are, the children of the warm world. Pointing our instruments at the cold one and learning from it. Tonight, you have traveled to the edge of the solar system. You have stood, in the mind, on a surface colder than any place on Earth, under a sky full of stars so sharp and clear they seem almost unreal, with a small gray moon drifting slowly overhead, and the Sun a brilliant point of white light too faint to warm you. You have learned the name of a god who tilted the world and flooded it with chaos, and discovered that the world named for him is also tilted, also displaced, also a monument to the forces that shape the solar system's early chaos. You have followed an orbit that takes 547 years to complete, that carries a world from the neighborhood of Neptune out to distances where light itself takes 12 hours to arrive. You have looked at a red surface built from 4.5 billion years of radiation chemistry, sitting silent and undisturbed, while every civilization that has ever existed on Earth rose and fell and was replaced and forgotten. And now, if you are still listening, you know something you did not know at the beginning of this journey. You know that the solar system is still being discovered, that worlds exist beyond Neptune in numbers we have not yet counted, that the ancient displaced objects of the scattered disk are not empty space or irrelevant debris, but real worlds with their own histories and chemistries and moons and orbits that speak of forces we are still working to understand. You know about Gonggong. And Gonggong, in the only way available to it, does not know about you. It continues, orbiting, red and ancient and silent, mass at the edge of everything, moving at 1.1 kilometers per second through a darkness so vast that the light from our sun takes over 12 hours to cross it, carrying the name of a god, carrying the records of 4.5 billion years, carrying its 9-headed moon in a slow gravitational conversation that will not be finished for billions of years more. Gonggong does not hurry. It does not need to. The universe has given it all the time there is. Rest now. The scattered disk is still out there, and Gonggong is still moving through it. As it has always moved, in the dark, in the cold, in the silence that has no end. This has been Science for Sleep. Thank you for traveling with us tonight.